Imagine a darkness so profound, so absolute, that it consumes everything in its path. A region of spacetime where gravity reigns supreme, where not even light can escape its clutches. This is the domain of a black hole, an object of immense density and gravitational pull. And some of these cosmic monsters are not content to simply exist. They are driven by an insatiable hunger, a thirst for matter and energy. Picture a lone star, adrift in the vast expanse of space. It wanders too close to this invisible predator. The black hole's gravitational grip tightens. The star stretches and distorts, its light warped and twisted. The star is torn apart, its remnants spiraling into the black hole's abyss. As the stellar material falls inward, it forms a swirling disk of superheated gas and dust. This is the accretion disk, a chaotic maelstrom of particles spiraling towards oblivion. Join us as we venture into their realms, exploring the science behind their insatiable appetites and the impact they have on the cosmos. Black holes, those enigmatic objects predicted by Einstein's theory of general relativity, are regions of spacetime where gravity is so strong that nothing, not even light, can escape their grasp. They are formed from the remnants of massive stars that have collapsed under their own gravity. Their density is unimaginable, but not all black holes are passive denizens of the cosmos. Some are active feeders drawing in surrounding matter with their immense gravitational pull. These are the accreting black holes, cosmic predators that relentlessly consume anything that strays too close. They are the ultimate cosmic vacuum cleaners, relentlessly sucking in gas, dust, and even entire stars. As material falls towards a black hole, it doesn't simply disappear into a void. Instead, it spirals inwards, forming a swirling disk of superheated gas and dust, the accretion disk. This disk is a chaotic and violent place, a maelstrom of particles colliding at incredible speeds. Accreting black holes are not just passive consumers, they are active engines that transform matter into energy with astonishing efficiency. Imagine a cosmic whirlpool, a swirling vortex of gas and dust heated to millions of degrees. This is an accretion disk, a defining feature of actively feeding black holes. Formed by material drawn in by the black hole's powerful gravity, accretion disks are not just visually stunning, they are crucial to understanding how black holes feed and grow. As matter falls towards a black hole, it doesn't plummet directly inwards. Instead, it spirals towards the center, much like water circling a drain. This spiraling motion is due to the conservation of angular momentum, a fundamental principle in physics. Think of a figure skater pulling their arms in during a spin. Their rotation speeds up as their mass is drawn closer to their axis of rotation. Similarly, the infalling material in an accretion disk spins faster as it gets closer to the black hole. This rapid rotation within the accretion disk generates immense friction between the particles of gas and dust. This friction heats the disk to incredible temperatures, often reaching millions of degrees Celsius, hotter than the core of our sun. These extreme temperatures cause the material in the accretion disk to emit electromagnetic radiation across the spectrum, from radio waves to X-rays and gamma rays. Among the most dramatic examples of accreting black holes are quasars and blazars, some of the most luminous and energetic objects in the universe. These cosmic beacons shine brightly across billions of light-years, signaling the presence of supermassive black holes at the hearts of distant galaxies. Quasars, short for quasi-stellar radio sources, were first discovered in the 1960s. They initially puzzled astronomers because they appeared as point-like sources of light, similar to stars, but emitted enormous amounts of energy, far exceeding the output of entire galaxies. The prevailing theory is that quasars are powered by supermassive black holes, millions to billions of times the mass of our sun, that are actively accreting matter at extraordinary rates. As gas and dust spiral into these black hole behemoths, the accretion disks heat up to extreme temperatures, generating the intense radiation observed from Earth. Blazars are a particular type of quasar where one of the powerful jets of energy emitted from the accretion disk happens to be pointed directly at Earth. These cosmic lighthouses are not only fascinating objects in their own right but also provide valuable insights into the early universe. Section 5. Tidal disruption events, when stars meet their end. In the cosmic ballet of black holes and stars, there are moments of extraordinary violence. Tidal disruption events, or TDEs, are among the most dramatic phenomena in the universe, marking the death throes of stars unfortunate enough to stray too close to a supermassive black hole. As a star approaches a black hole, the gravitational pull on the side of the star closer to the black hole becomes significantly stronger than the pull on the farther side. This difference in gravitational force, known as a tidal force, stretches the star, elongating it like a cosmic piece of spaghetti. If the star gets too close to the black hole, within what's known as the tidal disruption radius, these tidal forces become overwhelming, the star is no longer able to hold itself together. Section 6. Cosmic Gluttons, Ton 618, M87, and Cygnus X-1. The universe is home to a menagerie of black holes, each with its own unique characteristics and feeding habits. Some are relatively small and quiescent, while others are colossal gluttons, actively devouring matter and shaping the evolution of their surroundings. Ton 618, a hyperluminous quasar located billions of light-years away, takes the crown as one of the most massive black holes ever discovered. With an estimated mass of 66 billion times that of our Sun, this cosmic behemoth is a true monster, its insatiable appetite driving the intense luminosity that makes it visible across vast cosmic distances. M87, a giant elliptical galaxy located about 55 million light-years from Earth, harbors another supermassive black hole at its core. This black hole, with a mass of around 6.5 billion suns, was the first to be directly imaged by the Event Horizon Telescope in 2019. Section 7. Galactic Architects, Shaping Cosmic Destiny. Accreting black holes are not merely passive bystanders in the cosmic drama, they are active architects, shaping the evolution of galaxies and influencing the distribution of matter throughout the universe. One way in which accreting black holes shape their surroundings is through the powerful jets of energy and matter they launch into space. These jets, often traveling at near the speed of light, can extend for thousands of light-years, heating and pushing away gas clouds in their path. This process, known as feedback, can have a profound impact on star formation within a galaxy. By heating up gas clouds, these jets can prevent them from collapsing and forming new stars, effectively regulating the rate at which a galaxy grows. Section 8. The Eddington Limit. Can black holes overeat? Black holes are often depicted as cosmic vacuum cleaners, relentlessly consuming anything that ventures too close. But is there a limit to their appetite? Can these cosmic gluttons overeat? The answer, it turns out, is yes. There is a limit to how fast a black hole can accrete matter, known as the Eddington Limit, named after the British astrophysicist Sir Arthur Eddington. The Eddington Limit arises from the balance between the inward pull of gravity and the outward pressure of radiation emitted by the accreting material. As matter spirals towards a black hole, it heats up, emitting radiation that pushes outwards. If the black hole accretes too quickly, the outward radiation pressure can become so strong that it counteracts the inward pull of gravity, effectively pushing away in falling material and limiting the black hole's growth rate. The Eddington Limit is not an absolute barrier. Section 9. A Universe of Feasters, the Future of Black Hole Feeding. As we peer into the depths of space and time, we witness a universe teeming with black holes, from the stellar mass remnants of collapsed stars to the supermassive giants lurking at the hearts of galaxies. Their insatiable appetites continue to shape the cosmic landscape, driving the evolution of galaxies and influencing the distribution of matter and energy throughout the universe. In the near term, as galaxies merge and interact, black holes will encounter vast reservoirs of gas and dust, igniting periods of intense accretion and fueling the growth of these cosmic behemoths. These galactic mergers will trigger bursts of star formation, providing ample fuel for black holes to gorge upon. However, as the universe continues to expand and cool, the availability of fresh material for black holes to consume will dwindle. Section 10. Earth's Final Plunge, a Hypothetical Journey. Let's indulge in a thought experiment, a hypothetical journey to the edge of oblivion. Imagine Earth, our home planet, straying too close to a supermassive black hole, one perhaps lurking at the heart of our galaxy. What would befall our world as it plunges into the abyss? As Earth approaches the black hole, the tidal forces would begin to take hold. The side of our planet facing the black hole would experience a far stronger gravitational pull than the side facing away. This difference in force would stretch Earth, elongating it like a cosmic raindrop, a process known as spaghettification. As Earth ventures closer to the event horizon, the point of no return, the tidal forces would become increasingly extreme. Our planet would be stretched and distorted beyond recognition, its surface rippling and churning like a stormy sea. Eventually, Earth would cross the event horizon, the point at which gravity becomes so strong that nothing, not even light, can escape.